In this section, we're going to look at gravitational field. Gravitational field. Now, from Newton's law of gravitation, we've seen that any two objects exert force on each other with a force proportional to the product of the masses and inversely proportional to the square of the distance. But there's nothing in between them, and somehow these two objects exert forces on each other, okay? And that bothers some people. So another way of putting it is we can say this object is bringing about some change throughout space, and the change brought about by this object is exerting force on this one. That way of putting it is called field theory, okay? So instead of saying this object is exerting force on this object, we say this object brings about a change throughout space, okay, that we call gravitational field, and that field exerts force on this object, okay? So let's say field theory. Field theory. Instead of saying an object exerts gravitational force on another object, we say the object sets up gravitational field throughout space, and that field exerts force on an object placed at any point. So this is just another way of saying it, okay? Instead of saying that this object is miraculously exerting force on this object, even though there's nothing in between, we say this object sets up gravitational field throughout space, and that field that exerts force on this one. So this gravitational field is a property of space, okay? So there should be a field over there, whether there's an object over here or not. So it has to be defined in such a way that it's independent of the mass of the object placed at point P. So the field is a proper space. The field is a property of space, okay? It exists even though if there is no a particle at the point, okay? Now let's consider the field exerted by this object, okay? So it is a property of space. So in this case, we talk about a point, not an object. So this object over here is going to exert gravitational field at that point. And if we put a certain mass over here, then that field will exert force on this one. So it has to be defined in such a way that it's independent on an object placed over here. And the way we can do that is we can define to be gravitational per a unit mass. We can define to be the force on a unit mass placed at the point, okay? It is defined to be the gravitational force exerted on a unit mass placed at the point. In other words, this is defined to be gravitational force per unit mass. So if you use G for this field, let me use G for field, this G is defined to be gravitational force per unit mass. Okay? So using this formula, let's get an expression for it. Okay? So let's say the position vector of this point with respect to this object exerting the gravitational field. Let's say we put an arbitrary mass m prime over here, okay? And let's say this position vector is r. So we know that the gravitational force is going to be negative g m times m prime divided by r cubed times the position vector r, okay? Now the gravitational field at this point, we're talking about the gravitational field at this point now, is defined to be g divided by f g divided by m prime, okay? So that is negative g m prime r over r cubed divided by m prime, okay? So the m prime goes away, so we have the following formula for gravitational field. It's negative g m r divided by r cubed, okay? So this is gravitational field due to an object of mass m at a point whose position vector with respect to the center of the object is r, okay? Is r. All right, so this gives us, you've got a mass m over here, this is an object of mass m, and then this is a point. This is a point, and its position vector with respect to this object over here is r, okay? So this gives you the gravitational field at the point. Now, so as you can see, this is gravitational force divided by mass. This is basically the acceleration, the gravitational acceleration of an object placed at point B. So you can say that G is basically equal to the gravitational acceleration, because it's force per unit mass, gravitational acceleration of an object placed at point B, okay? So the field is basically the acceleration of an object placed at the point, because it's force divided by mass, okay? So gravitational force divided by mass gives you gravitational acceleration. All right, now this is by assuming the origin is placed at the given point, okay? How about if you want to use an arbitrary origin, okay? Suppose, let's say this is the object exerting the gravitational force, so mass m, and then this is our point over here, okay? But let's say we decided to use this coordinate system over here. Let's say this coordinate system over here, all right? And in the formula we have is, this is the position vector of the point at which we're calculating the field, okay, with respect to the object exerting the force. This is r. But if you use this coordinate system over here, then let's say the position vector over here is let's say r1, and the position vector of this one is, let's say, r2, okay? So from this triangle we see that r equals r2 minus, maybe I call this one rp, okay? Rp, this is the position vector of the point, rp minus r1, okay? So with that, we can write the formula for gravitational acceleration of gravitational field as follows. We can write this as negative g, the mass m, and then we got the vector rp minus the position vector of the object divided by the magnitude of this one, which is rp minus r1 cubed. Okay. Now let me make some changes in notation. Let me call the, let me write this a little bit differently. Let's say we have this object over here of mass m, and this is my point P. And let's say this is my coordinate system over here. So let me call this one, this vector over here, as the position of this object with respect to my origin. Let me call this one r prime. And let me call this position vector of this object r. Okay, then it follows that this position vector of this point with respect to the object exerting force would be r minus r prime. Okay, so with this notation we can write g as negative g, the mass m, and then you've got r minus r prime, okay, divided by the magnitude of r minus r prime cubed. Okay, so we can use this formula for gravitational acceleration or gravitational field. So in this formula, r is position vector, this is with respect to our origin, position vector of the center of the object, center of the object producing the field, and r prime is, this is position vector of the point at which the gravitational field is to be calculated. This is position vector of the point whose gravitational field is to be calculated. Gravitational field is to be calculated. Okay, so this is a general formula with an arbitrary origin. This is useful when you're dealing with the field due to a number of particles. Okay, for one particle you can just put the origin over here, and in that case you will just put this vector over here, the r prime, to 0. Okay, so this is a general formula with an arbitrary origin. If there are only two, if there let's say if there is only one object, it's easier to put the origin at the center of the object, which implies r prime is 0. So in that case, with r prime 0, we get the following formula: g equals negative g, the mass, you put r prime to 0, this vector to 0 over here, and you get negative gmr divided by r cubed. So this is if the origin is placed at the center of the object, provided the origin is at the center of the object, Okay, now let's look at an example. Let's say we have the following object. let's say its mass is maybe 1,000 kilograms, and I want to find the gravitational field at point P. Let's say this is maybe 100 meters away. Okay, so the question is, calculate the gravitational field, the gravitational field at point P. At point P, okay? So in this case, we have only one object, so it's easier to put the origin right at the center of this object, okay? So in that case, r prime would be 0. That is a position vector of this object with respect to the origin. And r, the position vector of this point, will just be this one over here, okay? So r is obviously 100 meters in the I direction, okay? And then of course our mass is 1,000 kilograms, okay? So that's it. And of course the magnitude of r, or r, is 100, okay? So with that we can easily calculate the gravitational fields at the given point. So you've got gravitational field equals negative g, the mass, times position vector divided by r cubed, okay? So that is negative 6.67 times 10 to the power of negative 11. The mass is 1,000 kilograms. The position vector is 100 in the I direction, divided by 100 cubed, okay? So it's basically negative 6.67. Then the power is, we got negative 11, we got 5 zeros over here, negative 6, and then we got negative 6 over here, so it's going to be 10 to the power of negative 12. 10 to the power of negative 12, and of course the unit is Newton per kilogram, okay? So this would be, of course, the direction is in the negative I direction, okay? So the directions of gravitational field and gravitational force are the same, all right? Okay, now we're going to look at superposition principle. How about if you have a number of objects in the vicinity of a point, okay? Let's say we're trying to calculate the field at this point, but then you have a number of objects over here around it, okay? So what you do is you calculate the gravitational field to each object, and then you add them vectorially, okay? Let's say it's m1, this is m2, this is m3, okay? If a number of objects are in the vicinity of a point, the net gravitational field at the point is the vector sum of all of the fields due to the individual objects, due to the individual objects or masses, okay? So basically the net field, let's say G net, let's say at point P, is simply G1 plus G2 and so on. You simply calculate the fields due to each object and then you add them vectorially, okay? So let Ri be the position vector due to the ice particle. Okay, and let R be the position vector of the point. Okay, so let's say this is our point P over here, and we've got maybe this particles over here around it. Let's say this is M1, let's say this is M2, let's say this is M3, and let's say we place our origin over here. Okay, so this would be my R1. Okay, this would be my R2, and this would be my my R3. Okay, and then the position of this one of the point, this is my R. Okay, so for example, this over here is R minus R1, this is R minus R1. Okay, this, the position vector of this particle, of this point with respect to this particle, this would be, this is R, this would be R minus R2, and so on. And this position vector over here would be R minus R3, and so on. Okay, so the G net would be like this. The G at point B, the net would be, the first one would be negative G M, that is R minus R1, divided by the magnitude of R minus R1 cubed. And then the second one will be negative G M R minus R2, divided by the magnitude of the position vector cubed, and this pattern continues. Okay, maybe we can factor out the common factor, which is GM. So we have the following: the gravitational field at point B, that's the net. We factor out negative GM, and then we have M R minus R1 over the magnitude of the position vector cubed. Oh, well, I factor out M, so in this one, and then plus R minus R2 over the magnitude of R minus R2 cubed, and so on. The same pattern continues. We close the bracket. Okay, or we can use summation to represent it. So the net gravitational field at point P is negative G times M, which is the summation of this one, R minus Ri, divided by R minus Ri cubed. Okay, so this would be the net gravitational field at the given point, that is using an arbitrary origin. All right, so we're going to look at an example. Suppose we have this coordinate system over here. Okay, let's say we have an object of mass maybe 1000 kilograms over here. Let's say we have another one over here, maybe 2000 kilograms. Okay, and let's say this distance is let's say 400 meters. This distance 400 meters, and then we're trying to calculate the field at point P. Okay, maybe point P is over here, and this distance is, let's say, 300 meters. Okay, so the question is, calculate the gravitational field at point P. Calculate the gravitational field at point P. Okay, so the net gravitational field at point P is, we've got two objects, M1 and M2, is G1 plus G2, and that'll be negative GM Let's factor out. Oh, no, this is, I couldn't factor out. The m's are different. They cannot be factored out over here. I made a mistake over here. These m's are actually different. Okay, it's supposed to be m1, m2. All right, so this cannot be factored out. So let me write this again. These are different masses, so I use the same mass over here, so they should be different masses. So this one is not right. So this one also is not right. So let me go to the next page. Let me take this out. Let me write it again. So we've got G net at point P is negative G m1 r minus r1 divided by r minus r1 cubed, and then minus G m2 r minus r2 divided by r minus r2 cubed, and so on. The same pattern continues. And if we factor G, then you've got G net at point P is negative G. We cannot factor out the mass. This is R minus R1 over R minus R1 cubed plus M2 R minus R2 over R minus R2 cubed, and the same pattern continues. And of course we can write this using summation at point P would be negative G, the summation of mi r minus ri divided by r minus ri cubed. Okay, so this is the correct formula. The masses cannot be factored out because they're different for the different particles. Okay, so in this formula, mi is mass of ice particle, ri is position vector of ice particle, and r is position vector of the point, position vector of the point at which the field is to be calculated, at which the field is to be calculated. All right, so this will be the right formula for the field. Okay, this is wrong. So this cannot be factored out. This is also wrong. So now let's write our example on the next page. Example. But let's say we have the following coordinate system. So let's say we have m1 over here, maybe 1,000 kilograms. We have m2 over here, maybe 2,000 kilograms. Let's say this distance over here is 400 meters. This distance over here is 400 meters, and we want to calculate the field at this point. That's our point P, and this distance, let's say, is 300 meters. Okay, so we want to find the net field at point P. The question is calculate the net field at point P. Okay, so we have two particles producing gravitational field at this point. So we've got the net field at point P is G, negative G, m1 r minus r1 over r minus r1 cubed, and then minus G m2 r minus r2 over r minus r2 cubed. Okay, so what do we know? We know M1 is 1000 kilograms. We know M2 is 2000 kilograms. Now this is our origin. So the position vector of M1 or R1 is this one over here, and that is 400 meters in the J. So R1 is 400 meters in the J direction. Okay, how about R2? The position vector of R2 is this one over here. This is R2, this is R1, this is R2, and R2 obviously is in the negative J direction. That's 400 in the negative J direction. All right, and R is the position vector of this point over here, which is 300 in the I direction. So R is 300 in the I direction. Okay, so that's all we need. So if we factor out G, so you've got G net at point P is negative 6.67 times 10 to the power of negative 11. Okay, and then we have M1. M1 is 1000 kilograms, and then we have R minus R1, okay, times R minus R1, this one over here. R is 300I and R1 is 400 in the J. So this would be 300 in the I minus 400 in the J. And the second one, the mass is 2000. Oh, I should say over the magnitude of this one. Well, the magnitude of this one is going to be 500. All right, let's do this. R minus R1 is 300 in the I minus 400 in the J, and the magnitude would be square root of 300 squared plus 400 squared, and that's going to be 500. All right, and R minus R2 is, we have 300 in the I, 300 in the I minus, and R2 is negative 400 in the J, so minus negative 400 in the J. Basically, this is 300 in the I plus 400 in the J, okay, and that implies the magnitude is 500. All right, so we have over 500 cubed over here, and the second term plus 2000, and then R minus Ri is over here, is 300 in the I plus 400 in the J, plus 400 in the J, the whole thing divided by the distance cubed, 500 cubed. Okay, so that's what you have to calculate. Now you see the power of 10 could be, this 500 cubed could be factored out. Also the power of 10, 3 zeros and 5 zeros could be factored out. So we've got negative 6.67 times 10 to the power of 5, and then you've got 500 cubed over here. Okay, so with that, we just have over here 3i minus 4j, okay, from this part over here, and over here we have 2. You see, we factor 1000, we have 2, 3 in the I plus 4 in the J. Okay, all right, and then of course this is negative 6.67 over 125. We've got 10 to the power of 6 over here, we've got 5 over here, so that's 10 to the power of negative 1. Okay, so we collect the i's, you get 3i, and then you've got 6i over here, so that is 9 in the I direction, and then we've got minus 4j plus 8j, negative 4j plus 8j, that is 4j. 4j. Okay, so this would be the force. You've got 3i plus 6i, that's 9i, and we have -4 plus 8, which 4, so this would be the gravitational field at point P. All right. Now next we're going to look at gravitational potential energy stored by two objects. Gravitational potential energy stored by two objects. Okay, so how do you know there's energy stored by two objects? Well, let's say we have two objects whose mass are capital M and small m. Okay, let's say a distance of r. Well, if you let them, what happens? They attract each other, so you get motion. That motion is coming from the potential energy stored between these two objects. Okay, so we want to get an expression for that energy. That is, how much energy would you get if you let these two objects lose? The amount of energy you get out of them would be equal to the gravitational energy stored by the two objects. Okay, so how we define the energy stored by these two objects is defined to be the amount of work you have to do to bring one of them from infinity to its location. Okay, so the gravitational energy stored by two objects, gravitational potential energy stored by two objects is defined to be the work required by an external force to bring one of the objects from infinity to its location. Okay, so let's say we're talking about these two objects. This is m and this is small m. Let's say this is r over here. All right, so the amount of work you have to do by an external force from infinity to this location is equal to the potential energy stored by these objects. Okay, so you see, when you bring this object, this is going attracted. Okay, so the external force has to pull, the gravitational force attracted, but we're just saying the work required, that is the work required to bring it from here to without accelerating. Okay, so we have to do zero work to bring, the net force should be 0. We have to bring this one with the minimum work required. Okay, so this, we have the gravitational force pulling this way, you got the external force opposing it, and so we have to move the particle without any acceleration. Okay, which means the work done by the external force plus the work done by gravity should be 0 if you're going to move it without any accelerations. Okay, so the work done by the external force should be the negative of the work done by gravity. Okay, so you remember the formula for work. The formula for work is the integral of force dot dr. Okay, from r1 to, let's say, to, well, r initial to r final. This is the definition of work. All right, so we're looking for the work done by the external force. So the work done by the external force equals the negative of the work done by gravity, or the negative of the integral of gravitational force dotted with dr. Okay, but what is gravitational force? The gravitational force is negative g let's say, so we have the mass m over here times the mass m divided by r cubed, and you've got the position vector r. This is the gravitational force. Okay, so the work done by the external force is the negative of this one, negative g m divided by r cubed, and then we have r dot er. Okay, now the work done is independent of the path followed, so we can just do the work in the direction of the position vector. So we can say r equals r in the direction of er. So r dotted with er is simply r. Okay, so we have w external equals these two negatives kill each other. So you've got g mass m divided by r cubed, and it's just r. Okay, and this integral goes from infinity to the location of the object, which is r. Okay, so that is the integral. Well, let me put the constant out, g m, the integral of 1 over r squared going from infinity to the location r. Okay, and the integral of 1 over squared is negative 1 over r, right? So this is negative g m m, so 1 over r going from infinity to the location r over here. Okay, so we have this external work is negative g m m, and this would be 1 over r minus 1 over infinity. So we get the external work, which is defined to be equal to the potential energy. We get this one, negative g m m. But according to our definition, this equals to the potential energy stored by the two objects. Oh, this is, let's say, or our potential energy stored by the two objects. So this gives us the following formula for the gravitational potential energy. Negative g, the product of the masses divided by the distance, is the formula for the gravitational potential energy stored by the two objects. It is negative because it is attractive energy. Energy is negative for attractive energy and positive for repulsive energy. Okay, so let's say example, let's say calculate the work done by gravity when an object of mass let's say 1000 kilograms is dropped from an altitude of, let's say, 1000 meters. Okay, so this is Earth, so this is the radius of Earth over here, radius of Earth, and so we have this altitude over here, which is 1000. Okay, so we want to calculate the work done by gravity when an object of mass is dropped from altitude of 1000 meters. Okay, so let the mass of Earth be me. Okay, so work done by a conservative force, if you remember, equals the negative of change in potential energy. So the work done by gravity would be the negative of UG final minus UG initial. Okay, so this would be the final, the initial distance, Ri, would be the radius of Earth plus 1000 meters. Okay, and the final would be the surface of Earth. Okay, so our final would be just the radius of Earth. Okay, so this would be the negative of, we have negative gm of Earth, the mass of the object, which is 1000. This is the final. Okay, so the final is simply the radius of Earth minus the initial. The initial is negative g mass of Earth, and then we've got this object over here, divided by the radius, the initial radius of Earth plus the altitude, which is 1000. Okay, so we can factor out the negatives. We can factor out g in the mass of Earth. Okay, so we've got g. Well, we can factor the mass of Earth, we can factor the 1000, and then this term would be negative would be positive. Okay, so it's going to be 1 over radius of Earth minus, this would be negative, it would be 1 over radius of Earth plus 1000. Okay, so this would be the work done by gravity. All right, now we can find this in the mass of Earth and the radius of Earth in tables in textbooks. Okay, all right, I think the mass of Earth is approximately 6 times 10 to the power of 24, and the radius of Earth is approximately 6 times 10 to the power of 6, I think. So with those numbers you can calculate the work done by gravity when object is dropped from an altitude of 1000 meters. All right, now we're going to look at principle of conservation of mechanical energy. Conservation of mechanical energy. Now, since gravitational force is conserved, then mechanical energy is conserved, right? So you've got mechanical energy initial equals mechanical energy final. All right, so in this case we have two objects. Let's see, we have an object of mass m and an object of mass m, okay, separated by r. So the kinetic energy is the sum of the kinetic energies of these two particles. Okay, but usually we deal with cases where one of the masses is much larger than the other masses. Okay, so if the mass of m is much bigger than mass m, this could be approximate to be at rest. If m is much bigger than m, the object of mass m can be assumed to be at rest. Can be assumed to be at rest. Okay, so if the speed of the object of mass m is v, the kinetic energy of the system is just half mv squared. Okay, so we know that mechanical energy is going to be kinetic energy plus potential energy. Okay, now the kinetic energy, we're assuming this is at rest, we have only the kinetic energy of this particle over here, which is half m v squared, and we just saw the gravitational potential energy of these two objects is negative g m small m divided by the distance separating them. Okay, so this implies, therefore, from conservation of mechanical energy, we can say half mass v initial squared minus g m m divided by the initial separating distance equals half m final speed squared minus g m m, and then the final separation between the two objects. Okay. All right. So let's say, example, let's say an object, let's say of mass of 100 kilograms is propelled upwards, let's say with a speed of, let's say, 100 meters per second. Okay, the question is how high will it rise? How high would it rise? Okay, so that's we have Earth over here. Let's say the mass Earth over here, and then it's being propelled from here with the speed of 100 meters per second. So the question is how high will it rise? Okay, and this is the radius of Earth. All right, so now the initial separation between the two objects is the radius of Earth. So you've got Ri is the radius of Earth, Re. Okay, and the initial speed is 100 meters per second. Okay, all right, and at the maximum height, Vf equals 0. At the maximum height, Vf equals 0. Okay, so we're looking basically for Rf, which is the maximum height. All right, so we have half m vi squared minus g mass of Earth, and the mass is 100 kilograms over here. This is also 100 over here, 100 kilograms, divided by the initial distance, which is the radius of Earth, equals, the speed is 0 at the final location, so you get minus g mass of Earth times 100, and the distance at the final location is, this is Rf, which is the radius of Earth plus the altitude. Okay, so that's what we're looking for, altitude we're looking for, and Rf equals the radius of Earth plus the altitude. All right, so that's it. So we've got this, well, the initial speed also we know is 100. So we have the following. We're looking for the altitude over here. So so this one is half times 100 times initial speed 100 squared. Okay, minus, we've got 100 g mass of Earth divided by the radius of Earth, that equals the negative of this one, me times 100 divided by the radius of Earth plus the height. All right, so well, we just have to plug in the values for the mass of Earth, for the radius of Earth, and we can calculate height from this equation. All right, so G is 6.67 times 10 to the power negative 11, and RE is approximately 6 times 10 to the power of 6, I think, and mass of Earth is approximately 6 times 10 to the power of 24, and of course G is 6.67 times 10 to the power negative 11. So from this equation, the altitude H can be calculated. Okay. Now we're going to look at objects in orbit. Okay. Kinetic energy and mechanical energy of objects in orbit that is moving in a circular in a circular path with a constant speed. So let's say we have an object of mass m, and then you've got this is revolving in a circular path over here. Okay, so in this case, the centripetal force is provided by the gravitational force. Okay, let's say this is an object of mass m, so centripetal force provided by gravitational force, provided by gravitational force. Okay, so of course we know kinetic energy is going to be of this object is going to be half m v squared. Okay, now to obtain this speed, we're going to say centripetal force Fc equals the gravitational force, and that is m speed squared divided by r. That's the distance between this, equals g m capital M divided by r squared. Okay, so from that we can get an expression for the speed. So you've got this m goes away, and then this r goes away, so you get v squared is basically g m divided by r. Okay, so it follows that the kinetic energy of an object in orbit is half mass times the square of the speed, which is g m over r. Okay, so we got the following: kinetic energy equals half g m over r. Okay, so this is the formula for the kinetic energy of an object in orbit at a distance r from the center of the massive object of mass m. All right, but also remember that U equals negative g mm over r, so this implies kinetic energy equals negative half of U. Okay, so there's a very simple relationship between the kinetic energy and the potential energy. Okay, now let's look at mechanical energy. Mechanical energy is the sum of kinetic energy and potential energy, right? So we just concluded the kinetic energy is half of U, or half g mm over r, and the potential energy is negative g mm by the distance. Okay, so this is equal to negative half g, the product of the masses, divided by the distance. Okay, that's the formula for mechanical energy: negative half g mm divided by the distance. All right, so this is a formula for mechanical energy, but remember, but U also equals negative g mm divided by r, so this also implies mechanical energy is half of potential energy. Okay, so you see, so we have the following: mechanical energy is half of potential energy for objects in orbit, potential energy, and kinetic energy is the negative of half of potential energy. Potential energy. So there's a very simple relationship between mechanical energy, potential energy, and kinetic energy for objects in orbit. Okay, and also mechanical energy and kinetic energy are negatives of each other. Okay, also mechanical energy is simply the negative of kinetic energy. All right. Example. Calculate the potential energy, kinetic energy, and mechanical energy of a satellite of mass 10,000 kilograms revolving, let's say, at an altitude of, let's say, 1,000 meters. Okay, so let's say this is Earth. Let's say satellites over here. So we're saying is this is the radius of Earth, and this is the altitude h equals 1,000 meters. All right. So the potential energy is negative gmm. It's the mass of Earth. It's the mass of satellite divided by the distance, or negative g mass of Earth, the mass of satellite divided by the radius of Earth plus the altitude 1,000. Okay, so the mass of the satellite is 10,000. So you've got this is negative 6.67 times the mass of Earth. Mass of the satellite is about 10,000, and then we divide this by the sum of radius of Earth and 1,000. Okay, this is times 10 to the power of negative 11 joules. So this is the energy. We just have to plug in the mass of Earth and the radius of Earth, which is available from tables in textbooks. And then kinetic energy is the negative half of u, half of this, and mechanical energy is simply half of this. Okay, all right. So finally, we're going to look at escape velocity. Escape velocity. Okay, so this is the velocity by which an object is propelled from the surface of the Earth, for which it will never come back. Okay, so this is the minimum velocity for which, when an object is propelled upwards, it will never come back. It will never come back. Okay, so let's say this is the surface of Earth. If this object is propelled with this velocity that we call escape velocity, it will never come back. Okay, so what this means is, since the minimum velocity, the object should have zero velocity at a point where the object is free from gravity. So this implies the object will have zero velocity. This is because we're talking about the minimum velocity. Minimum velocity. Okay. When it is free from gravity. It is free for gravity. Of course, if it's not zero, it means we're talking about velocities higher than escape velocity, but we're looking for the minimum. Okay. And it's free from gravity when the final location is infinity, and it is free from gravity when RF is infinity. Okay, so from the conservation of mechanical energy, we have the following: half m vi squared, and then minus gm, we're talking about an object, let's say of mass m over here, m over initial I equals half m v final squared minus gm m over rf. Okay, so we're saying the initial velocity, when the initial velocity is the escape velocity, that's the minimum velocity at rf equals infinity, then it follows that vf equals 0. Our initial distance is the radius of Earth, and then of course it will be free from gravity when RF is infinity. Okay, so with that we have half mass v escape velocity squared minus gmm over the radius of Earth equals, this term would be 0, this also will be 0, gmm divided by infinity also will be 0. So it follows that, and as you can see, the mass of the object will cancel out. So you've got half of v escape squared equals gm mass of Earth divided by the radius of Earth, So the square of the escape velocity is 2 times g, the mass of Earth, divided by the radius of Earth. So this is the minimum velocity for which the object will never come back when it's propelled from the surface of Earth. Okay, the radius of Earth. All right. When you put the values for, this is a constant. Let's see. When you put the values for mass of Earth, radius of Earth, this turns out to be 1.1 times 10 to the power of 4 meters per second. Okay, so this is the escape velocity from the surface of Earth. It just depends on the radius of Earth and the mass of Earth. Okay.